we need AI. And so that's actually the biggest danger, is that we don't use it where we need it in society.
Why did Jack Rer, the CEO of Sandbox AQ, say that the biggest danger is not using AI? Sanctions and restrictions in states like California could threaten the US tech dominance and allow other countries to play catch-up. But the new state-of-the-art quantitative AI using LQMs instead of LLMs might forever change that. So if you want to learn how AI could reshape government and large corporations across the US, then keep on watching. Jack Rer is making the case that we need large quantitative models, LQM, instead of just large language models, LLM, when it comes to creating future products. Why? Because LLMs, like ChatGPT, are great at processing and generating text, but they don't actually understand the hard math, physics, and chemistry that drive real-world innovation. Rer points out that most of the economy isn't just about words, it's about numbers and quantitative relationships. If you're trying to develop a new drug, optimize financial models, or create breakthrough materials for industries like aerospace or automotive, you need AI that understands equations, simulations, and complex data, not just words. That's where LQMs come in. So while LLMs are great for tasks like writing, brainstorming, and summarizing, LQMs are built to crunch numbers, simulate real-world phenomena, and solve hard scientific problems. That's why Rer believes they're the key to the next wave of innovation. But is Rer actually correct? And will LQMs be the future of AI? Well, to understand that, we first need to understand what large quantitative models are. Because dealing with LLMs and LQMs can be a little difficult sometimes. Here's how I like to think about them. LLMs and LQMs are like two different kinds of chefs in a futuristic kitchen. An LLM is like a chef who can smash that like button, just like you should if you haven't done so already. But no, in all seriousness, an LLM is like a chef who has read every cookbook ever written. If you ask them to make a dish, they can describe recipes in great detail, suggest ingredient substitutions, and even come up with creative new dishes based on patterns they've seen before. But here's the thing, they don't actually understand how the food reacts when it's cooked. They can't predict how heat changes a sauce's texture or how a specific chemical reaction creates new flavors. They're just really good at describing and remixing existing knowledge. An LQM, on the other hand, is like a chef who's also a food scientist. They don't just know recipes, they understand why food behaves the way it does. If you give them a new ingredient, they can simulate how it will react at different temperatures, predict how the flavors will blend, and even invent entirely new cooking techniques based on the underlying chemistry. Instead of just copying and remixing, they're creating and testing in a way that's grounded in real-world science. Now, if we take this a step further and replace futuristic kitchen with artificial intelligence, then we would understand that LLMs, like ChatGPT, are great for processing and generating language, just like the recipe-savvy chef who can describe and refine ideas. Whereas LQMs actually understand and simulate real-world data, like the food scientist who experiments and discovers new possibilities. That's why LQMs are so powerful for fields like science and engineering. They don't just repeat what's been done before. They model reality, run experiments, and create things that have never existed. This is why Rer said that they will be the key to product development in the future. If you're trying to develop a new product, whether LLMs or LQMs are better, really depends on what kind of product you're making. LLMs, like ChatGPT, are amazing when it comes to anything involving text, language, and creativity. They're great for brainstorming ideas, writing marketing materials, generating code, or even summarizing research papers. If your product is content-driven, like an AI writing tool, a chatbot, or a coding assistant, LLMs are a solid choice. But here's the catch. LLMs don't actually understand math, physics, or chemistry. They work by predicting words, not by running real-world simulations. That's where LQMs come in. Unlike LLMs, LQMs are designed to handle numbers, equations, and complex quantitative relationships. So if you're working on something like drug discovery, financial modeling, or designing new materials for aerospace or automotive industries, an LQM is going to be way more useful. So which one is better for product development? If your product is about communication, creativity, or software, LLMs are probably the way to go. But if you're dealing with hardcore science, engineering, or anything that requires serious number crunching, LQMs are the real game changer. In some cases, combining both could be the best approach. Imagine an AI that not only runs complex simulations, but also explains the results in plain English. Now that's next-level innovation. LQMs are better for science and engineering because they deal with real-world numbers, equations, and physical laws rather than just predicting text like LLMs do. Science and engineering aren't about guessing the next word in a sentence. They're about understanding and modeling complex systems like chemical reactions, material properties, financial risks, and climate patterns. Take drug discovery, for example. If you're trying to design a new cancer treatment, you don't just need to summarize research papers, which LLMs can do. You need an AI that can simulate molecular interactions, predict how a drug will bind to a protein, and optimize chemical structures for effectiveness and safety. That's what an LQM can do. The same goes for engineering. If you're designing a new jet engine, an LLM might help you write a report about it, but it won't be able to simulate airflow, heat distribution, or material stress. An LQM, on the other hand, can run these calculations based on physics and real-world data, making it far more useful for building and testing actual products. Essentially, LQMs don't just talk about science and engineering, they do the math behind them. And in fields where precision, accuracy, and real-world modeling matter, that's a game changer. So if it's such a game changer, why haven't these computer engineers been building LQMs from the get-go? I mean, who wouldn't want to have a computer that can discover revolutionary drugs that can cure all sorts of diseases? Even though they are so powerful, building these large quantitative models is no small feat. They're complex and nearly impossible to build, which is why we need a lot of time. Building LQMs has been way harder than building LLMs, and that's why we haven't seen them take off until now. The biggest issue: data. LLMs are trained on text, which is everywhere: books, websites, Wikipedia. But LQMs need high-quality scientific data, and that's much harder to get. A lot of it comes from complex simulations, lab experiments, or proprietary research locked away by companies and universities. You can't just scrape the internet and expect to build a great LQM. Then, there's the sheer computational power needed. LLMs predict words based on patterns, but LQMs have to simulate reality. Things like molecular interactions, material properties, and economic models. That takes way more processing power, often requiring specialized hardware like quantum computers or supercomputers. Even today, running those kinds of simulations is expensive and time-consuming. Another challenge is that LQMs have to follow the actual laws of physics, chemistry, and biology. With LLMs, if a sentence sounds right, it's good enough. But with LQMs, there's no room for error. You can't just guess at how a new drug molecule will behave or how a material will react under stress. The model needs to be scientifically accurate, which makes designing and training it much more complex. On top of that, you need actual experts in physics, chemistry, and engineering to help build these models. LLMs mostly rely on machine learning engineers and massive text data sets, but LQMs require deep collaboration between AI researchers and domain experts, which slows things down. And unlike LLMs, where we already have established architectures like transformers, LQMs still don't have a clear, standardized approach. Researchers are experimenting with different methods, some using physics-based neural networks, others trying quantum-inspired models, but there's no one-size-fits-all solution yet. So why are we finally seeing LQMs now? Well, we're at a turning point. Better AI hardware, more accessible scientific data, and smarter hybrid AI techniques are making them possible in ways they weren't before. It's still a tough challenge, but for the first time, we actually have the tools to start building them at scale. But is this enough to build a good LQM? In a good case scenario, LQMs could revolutionize healthcare by speeding up drug discovery and enabling personalized treatments, like targeted cancer therapies, saving millions of lives. They could also drive breakthroughs in materials science and sustainable energy. That being said, in a bad case scenario, LQMs might be misused, leading to unintended consequences. For instance, they could be used to create self-replicating machines or optimize production in ways that harm the environment or exacerbate inequality. Without proper oversight, these technologies might worsen issues like climate change or social disparity, creating more problems than they solve. Careful regulation is essential. Here's another video AI enthusiasts loved watching. This is AI Exposed, demystifying the world of artificial intelligence, one video at a time.